This is part 2 of comparing linear, exponential, and quadratic functions. We're up to example 3 where it says write a function that models the data. So the first thing we need to do is see if we have a constant difference between our x values. And if we look here, 0 to 1, 1 to 2, we're adding 1 each time. So there is that constant difference between our x values. Now we have to look at our y values. From 12 to 0, that's going to be negative 12. From 0 to 4, 0 to negative 4 is negative 4. Negative 4 to 0 is plus 4. And from 0 to 12 is plus 12. All right, so that's not a common difference. It's also not a common ratio, meaning that it multiplies by a common number to get to the next term. So now we're going to have to look at our second common difference to see if the second differences are common, which would make it quadratic. So negative 12 to negative 4, that's an increase of 8. From negative 4 to 4 is an increase of 8. And from 4 to 12 is an increase of 8. So you can see that this is our second difference. This is our first difference. And so when our second differences are constant, we can determine that this is a quadratic function. So this is quadratic. And we looked at several different ways previously to write quadratic functions. We've looked at standard form and vertex form and factored form. So looking at, well, factored form is also called intercept form. So we're going to look at what we're given in the table. So we're given 0, 12, 1, 0, 2, negative 4, 3, 0, and 4, 12. Because we have 1, 0, and 3, 0, we know that we have two x-intercepts that are given. So if we do factored form, or better known as intercept form with this curriculum, we can rewrite an equation using that form. So we're going to start by writing down the general formula. So y equals a times x minus p times x minus q. And I call this factored form because it looks like factors, but again, they call it intercept form. All right, so our x-intercepts again, we can see here are 1 and 0 and 3 and 0. All right, so I'm going to substitute those for p and q. So I'm going to have y equals a times x minus 1 and x minus 3. So all I have to do is take the numbers from the table, plug it into my factored form or intercept form, and I know because my y values are 0, I know this is my x-intercept, because if you graph this point, it would be 1, 0, which means it does not go up or down. It's just at 1 on the x-axis. So that's why it's the x-intercept. Now, we can choose any other point in the table to plug in for x and y, so we can solve for a. So let's use 0, 12. So my x is 0, my y is 12. F of x, remember, is the same as y. So I'm going to come down here, and I'm going to take this equation. I'm going to plug in 12, and I got a. And then for x, I'm going to plug in 0. So 0 minus 1, and 0 minus 3, and then we can solve. So I'm going to have 12 equals a times negative 1 times negative 3. Negative 1 times negative 3 is 3. So I've got 3a equals 12 divided by 3. So a equals 4. All right, once we know what a is, we have a and we have our intercepts, so we can take this general formula now and plug in a, p, and q, and that gives us an equation. So y equals 4 times x minus 1 times x minus 3. That's an equation in intercept form or factored form, but let's write it in standard form. So how do we put it in standard form? We simply multiply it out. So let's leave the 4 here for a second and multiply the two binomials. X times x is x squared, minus 3x, and minus 1x is minus 4x. Negative 1 times negative 3 is plus 3. Now we multiply by 4. Each term is multiplied by 4, so 4 times x squared, 4 times negative 4, and 4 times 3. And if I did all my math correctly, this is an equation in standard form that represents this table. All right, so this is called a function that models the data. So why is it a function? Because I can write this as f of x. So if I want to write this as f of x, I can. I use y most of the time because it's easier to write, but f of x is just function notation for this. So this would be a function that models the data for that table. You can see that it's quadratic, and we determined it was quadratic right off the bat because of the second difference. And don't forget your study tip to check your function in example 3. Substitute the other points from the table to verify that they satisfy the function. So you could take x is 2 and y is negative 4, plug in your points for x and y here, and if it comes out to be left side equals the right side, which means it's a true function, it's a true statement, then it would satisfy the equation. Also, x is 4 and y is 12. You could plug those values in as well to check this equation. All right, I don't have much room left on here for example 4, but it says write a recursive rule for the quadratic function f in example 3. So the reason I have this on here is because we're looking at this in order to write this one. All right, so you can see that a recursive rule is something that we've already done for linear and exponential functions, but now this is a quadratic function, but it's going to be very similar. So you can say an expression for the nth term of the sequence of the first difference is negative 12. You can see right here, this was negative 12. So we can say we have negative 12, and we're going to have plus, and then we know that our common difference here is 8. So it's going to be 8 times n minus 1. All right, if we multiply that out, we can go ahead and say negative 12 plus 8n minus 8. That's equivalent to 8n minus 20, because negative 12 and negative 8 can be combined into negative 20. So 8n minus 20. All right, so how do we write that? We can write that as a recursive rule. Remember, you got to have your first term. So we're going to have f of 0 equals f of 0. If you come over here and look, that equals 12. And then the rule would come after that. So we're going to have f of n equals f of n minus 1 plus 8n minus 20. So that's the rule we found right here. But remember, when you're writing a recursive rule, you have to identify that first term. And then this signifies that you're looking at your previous term plus 8n minus 20. That is a 20 there. All right, so f of n minus 1, remember that just is math notation to represent n minus 1 represents the previous term, not n, but n minus 1, so the one before it. Example 5, using and interpreting average rate of change. 2 social media networks open their memberships to the public. Compare the network memberships by calculating and interpreting the average rate of change from day 10 to day 20. All right, if we look at the table, we can see it has day 0, day 5, 10, 15, 20, 25. So it says day X, that's our days. Members are Y, okay? And it says how many members. Day 0 had 650 members, day 5 had 1,025, and so on. So this says we need to look at the average rate of change from day 10 to day 20. So these 2 points are the only 2 points that we really need to look at right now. So remember, average rate of change is your difference in y's over your difference in x's. All right, and it was written as f of x minus f of x, or f of b minus f of a, I think before. It's the same thing as difference in y's over difference in x's. So right here's my y values. So I just need to do the difference in y's. So I'm going to have 2150 minus 1400. And then I'm going to do 20 minus 10. All right, 2150 minus 1400 is 750 over 20 minus 10 is 10. And I can reduce that and I get 75. All right, so my average rate of change is 75 members per day for network A, because this is network A right here. All right, now 2 social media networks. So we're supposed to be comparing. Remember, comparing the networks. So we're going to put network A here, so we don't forget that that's network A. And let's change to white here so it makes it a little easier. So let's look at network B. All right, network B gives us a graph. So let's look at the graph. So let's look. I'm going to put this in red. We want to still look at the average rate of change between days 10 and days 20. So on day 10, the membership is about here. And day 20, the membership is up here. All right, so what numbers are we going to use? We're going to have to use kind of an estimate here because it's not an exact number. So let's say this is 10, and if this is 600 and this is 1200, that means this is about 900. It looks like it's just below 900. Let's just use 900. So we're going to say 10, 900 is 1 point. And then we're going to say 20, and let's say 1800. So 20 and 1800. Put my comma in the wrong spot. All right, 20 and 1800, and then I'm going to do the average rate of change the same way. So I'm going to say 1800 minus 900, that's my change in y's. And then 20 minus 10, that's my change in x's. 1800 minus 900 is going to be 900. 20 minus 10 is 10. That's going to be about 90. All right, so we've got 75 for A, and we've got 90 for B. So when it says compare the 2 networks, you can say from day 10 to day 20, network A membership increased at an average rate of 75 people per day, and network B membership increased at an average rate of change of 90 people per day. So we can conclude that network B membership is growing faster from days 10 to day 20. Now, if you look at this graph and you put numbers that are slightly different, maybe you say this isn't quite 900, you put something else, you're going to get something slightly different. But when you're looking at a graph that's not exact numbers, you're just going to do your best estimate. So that is how you interpret these 2 pieces of data, our table and our graph. And this is how we use the average rate of change to compare those 2 memberships.